All right, let's get started. So last time, Tatsu talked about scaling laws, and we're going to take a little bit break from that and talk about an inference. So the problem of inference is very simple. You've trained a model, and you're given a prompt, and you want to produce the response, usually as accurately and as quickly as you can. So inference turns out to be only one lecture, but it's actually of growing importance. And it shows up in many places. So clearly, once you've trained a model, you don't just sit there and if you're a researcher, you put a plot in your paper of here's how my model works. But for everyone else, you actually want to use this model. So what does use look like? It could be chatting with an AI assistant or a chatbot. It could be doing code completion. These days, agents are very popular, and that requires inference. Batch data processing as well. It's also used for evaluation, for evaluation that requires generation in particular. And it's also used inside training. If you're doing reinforcement learning, you need to have a model, you generate rollouts, and you score them, and you update the weights appropriately. So inference shows up all over the place. And efficiency as is the theme of this class really matters more than ever here. And even if you just look at the actual use vantage point, training is a one-time cost. It could be very expensive. It is very expensive. But once you're done with it, that's it. But inference is a repeated cost. You kind of incur it every single day. OpenAI is estimated to produce 8.6 trillion tokens a day. And just for reference, DeepSeek v4, which came out earlier this year, was trained on 32 trillion tokens. So in less than 4 days, the number of tokens that OpenAI has to produce, and therefore the compute is at least a DeepSeek v4. And of course, even the frontier models might be trained on more tokens, but still inference, the number of tokens generated is going to be higher. So that's just some perspective. And moreover, I think the importance of inference has grown in the last year because once upon a time, we thought of language models as primarily as chatbots or assistants, where you put in a prompt, you get back a response, and presumably the goal of the human is to read the response. But now as we move more into an agentic world, what it looks like is that a query goes in, and the agent is going to do a bunch of stuff. It's going to think, it's going to reason, it's going to call some tools, it's going to introspect, and at the end of the day, it will produce some output for a human to read. So most of the tokens that the agent produces is actually not for reading. And so you should really think about the number of tokens generated as really the compute spent. And there's no sort of limit. If you have an ambitious enough problem, you're going to need much compute and a lot of tokens. Right? So if you were in the chatbot world, maybe inference, after a certain point, it's fast enough because humans can only read so fast. But for an agent, there's no kind of limit to how much value you can get out of squeezing more out of inference. So there's a lot of people doing inference. On the commercial side, of course, all the closed API providers have to serve their models, so inference is a big deal for them. And there is also a bunch of providers serving open weight models and providing inference as well. And in the open source community, there's a bunch of packages. So VLM is probably a popular one, kind of a go-to. SGLang is another one that's particularly good for agentic workloads, but maybe not as popular yet. And then there's TensorRT from NVIDIA, which is really fast, but it's more narrow. And then Llama CPP, if you want to run inference on your on CPU, this is a popular package. Okay, so hopefully I've argued that inference is huge. If you can make inference twice as fast or even 10% faster, that is a big deal. So now the question is, what does fast mean? So there's a few metrics that capture the notion of fast, and they're going to be applicable in different settings and have different trade-offs. So one metric of fast is time to first token, or TTFT. This is essentially how long a user waits before any generation happens. So you put in a query into ChatGPT, and some number of milliseconds passes by, and then from the point the first token comes in, that is the time. And this is generally useful for interactive applications because that latency where you're just waiting and doing nothing is the longer that is, the worse the user experience. And as soon as tokens come in, it doesn't maybe have to be that fast because if you're going to read it anyway, you can't read that fast. So the second metric is latency. And this is from the standpoint of an individual user, how fast are tokens appearing for one query. This is also important for interactive applications. So basically, this is how fast the tokens are kind of streaming through. And then a second related concept is throughput, measuring tokens per second. This is how fast tokens are appearing for many queries. So latency, or 1 over latency, and throughput are clearly very related, right? It's very kind of aligned. In general, many interventions will make latency and throughput better. But as we'll see later, there's actually a trade-off here. And throughput is useful for if you're doing a bunch of batch processing, right? You have a petabyte of data and you want to process it with a language model. You just want that job to get done. It doesn't matter if one query is coming in faster, sooner, or later. Okay. So what determines the efficiency by any of these metrics of inference? So the high-level bit is as follows. And this is kind of maybe one high-level bit to remember from the lecture is that when you're doing training, you see all the tokens at once because in supervised fine-tuning, you see all the tokens, and you can parallelize over the sequence. Remember, think about in the transformer, the calculation for attention MLP, the sequence is just a dimension, so it's a big tensor that gets multiplied, and so you essentially process all the tokens at once. In inference, you can't do that. You have to generate, because of the autoregressive nature of inference, tokens sequentially, one at a time. So this is a fundamental problem of why inference is a very different workload than training, because you can't parallelize across the sequence dimension. And therefore, as we'll see later, it's going to be harder to have high arithmetic intensity or fully utilize the compute. Okay. All right, so let's go on. So first, I'm going to just maybe a preview of what's in this lecture. First, I'm going to do some math to understand the arithmetic intensity and throughput and latency, how to think about that for a transformer. And then I'm going to talk about various techniques to reduce the cost by making the KV cache smaller, quantizing model pruning, and then finally I'll talk about speculative decoding and then some kind of practical concerns. All right, so this is going to be a bit of a review, mostly kind of swapping in, make sure we're on the same page with respect to notation. Much of this lecture is based on the scaling book from Google on transformers and inference. So I do recommend that people go check it out. It's very nicely written, and some of the figures are generously lifted from that book. Okay, so just to establish a bit of notation to understand this diagram. So we're going to use symbols, think about in INOPS, to denote dimensions, but also their kind of length. So B is going to be the batch dimension and also the number of sequences. T is going to be the sequence dimension, which is also the number of tokens. D is the model dimension. H is the head dimension. Okay, so if I'm going to write this, this is taking a product between a tensor with dimensions B, T, and D, and another matrix of D and H, and I produce B, T, H. So what is going on here is that there are some dimensions marked red, which are going to be contracting. These dimensions appear in both operands and disappear from the results. And then there's going to be other regular dimensions in black that appear only in one operand and stay in the result. Okay, so this is kind of the general form. Another case is if you have blue dimensions, that means they're batching dimensions, and they appear in both, but stay in the result. They do not get contracted or reduced. Okay, so the interpretation here, as we'll see later, is that we have this tensor for every sequence and token position. You have a vector, and you want to multiply that by a matrix. And then here, you're basically taking a bunch of dot products between two tensors. Okay, so with that in mind, this in all its full glory is the description of a transformer block. So it looks a little bit like a circuit diagram. There's a lot of details here, but I actually find this probably the most kind of crisp definition of what a transformer is. You see a lot of description of a transformer, and frankly, a lot of them are kind of, it's hard to understand what is exactly happening. This one basically tells you exactly the shapes of the tensors and allows you to reason about the dependency. So for a transformer block, you take the X, which is the activations of one layer, you feed it through attention, and then you feed it through an MLP. And just as a kind of a quick refresher, the X you project it using a query matrix, a key matrix, and a value matrix. You'll see here that we have n, which is the number of heads, and h is the dimension of each head. So the query matrix is batch times sequence times number of heads times the head dimension. And k and v, instead of having n, we have k, which we'll see later, which we have a potentially smaller number of key value heads. And then this is the attention operation where notice that there's batching dimensions. So b appears in both, and we're contracting over the head dimension. And we'll come back to why this b being in both makes inference hard, why attention is kind of a bottleneck there. Okay, so just kind of hold on to that thought. And the MLP is kind of very simple and straightforward. You just do some map malls. This is the gating matrix. This is the up projection and a down projection. So I think you guys have implemented this, so I don't want to belabor it, but just to swap in the notation. By convention, we're going to assume that in the MLP, the MLP up projects the d-dimensional model dimension into 4 times that. So f is always, think about it as 4d whenever you see f. And then the model dimension gets split across the n heads. So the model dimension is always equal to number of heads times the head dimension. And then the number of heads gets split in the case of group query attention into the number of groups and the number of heads per group. And finally, we have 2 variables, s and t, which both represents the kind of the sequence dimension. And the difference is that s is going to be represent the number of input tokens and t is going to represent the number of output tokens. So in training time, these 2 are the same because we're predicting all the same inputs as outputs. At inference time, t is going to be 1 and s is going to be the input. Okay, so another review for arithmetic intensity. So I talked about this in the second lecture. So just as a warm-up, suppose I'm multiplying 2 matrices, a b by d matrix and a d by f matrix. So in tuition, b is the batch dimension, d is the hidden dimension or the model dimension, and f is the up projection dimension in the MLP. So remember, what is arithmetic intensity? I have to count flops, and I have to count the amount of memory moved. Okay, so we can do this as follows. So what do you have to do to multiply these matrices? Now remember the system's lectures, you have to read X from HBM. And if you're storing everything in BF16, which is the case for inference, we're going to have 2 times B times D. You're going to read W. That's going to be another 2 times D times F. You're going to do the map-mul. So that's number of flops is 2 times B times D times F. And then you're going to write it back. Okay? So every time you read and write, it's basically the number of entries. It's a kind of a quadratic-like term. And map-muls are cubic. And remember, this is going to be important because that's how you're going to get high arithmetic intensity. So total number of flops is the cubic, and then the bytes transferred is the sum of the reads and writes. Okay, so remember arithmetic intensity is how much compute we do per byte transfer, and we want this to be high. So the intensity is going to be equal to flops over bytes transferred. And I'm representing all these things symbolically because it will be easier to see and work with rather than numbers. One kind of just simplification we can make is that suppose that the batch dimension here is much less than D and F, then we can simplify this. So in particular, what this is doing is saying D equals C times B and F equals C times B, and let C go to infinity. So both D and F are really large and B is smaller. And this just reduces to the intensity of B. Okay, so the upshot of that is that remember when we did arithmetic intensity for map-mul, it was something like n over 3. And this is kind of the analog where instead of just having one variable for having square matrices, we have non-square matrices. Okay, so just to compare, so the accelerator intensity of hardware is you look at the flops per second in the spec sheet. You look at how much memory bandwidth, how fast memory gets moved between HBM. You divide, and that is the accelerator intensity. And now you compare your computations intensity with your accelerator intensity. And if it's greater, then you're compute bound, which is good. If you're less, then you're memory bound, and that's bad. So in this case, for H100, for this particular map-mul operation, you're compute bound if the batch size is greater than 295. So here's an extreme case. So suppose you just have one example. Okay, what happens if you have one example? Then your arithmetic intensity is going to be 1, and this is going to be memory bound. And you can kind of see what's going on here. You're reading this DF matrix, but B is only 1, so you're effectively doing only 2 times D times F flops. So that's, and this is basically kind of the workload that you'll see in inference. You don't get these like full matrices, you get these like very thin matrices or tensors. Okay, let me stop there in case there's any questions. Yeah.
In the transformer slide, I just want to confirm. Sorry, the next across these groups. Yes, can search across. You actually just crossed over. Yeah. Should that be across K groups instead of G groups?
I'm having trouble with the connection.
Let's see. So the number of groups here is, wait, I'm just making sure. So K is the number of key value heads. And so you have G, is that G per KV head. So
My understanding is like each key had will have a few words.
yeah.
Correspond to it. And if we break down the N into AG, then that means G is the number per I per T. That means we have K groups. That's my question.
Okay, so I think you're right. So K should be the number of groups, and G should be the number of the heads per one of those groups. Yeah, okay. Thanks for that. I'll fix that later. Okay. So let's talk a little bit more about the arithmetic intensity of inference. Okay, so here's how to think about what's happening in inference. Let's say you just do it naively. So here is a prompt, never gonna give you, going to the transformer, and the transformer generates keys and values and activations, and at the end of the day, it generates logits over the output vocabulary, and you sample a token, and that token gets concatenated with the prompt, and then you just do this again. You generate never, you attach that to the prompt, and so on and so forth. Okay, so this is the most naive thing. If you have a black box that takes a sequence and outputs a distribution of tokens, which is exactly what a transformer does, you can just apply this repeatedly. Okay, so this is works, but this is really bad because each time you generate one token, you actually take order t squared time, where t is the number of tokens that you've generated so far. So generating t tokens is actually t cubed. Okay, because the attention is already t squared, and you have to do that, once for every token. So this is pretty bad. But the observation is that you don't actually have to do this. A lot of the work can actually be shared across prefixes. So for example, if you're over generating never versus you're generating up, you're actually computing a lot of the same key values for never gonna give. So these tokens, they shouldn't change. Okay? And this is because it's a causal transformer. It was bidirectional, then if you attach a token, then everything changes. But if it's causal, then the activations here don't change based on any tokens you append. So with that observation, the first obvious thing is to store a KV cache in HPM so that between successive token generations, you can just reuse the KV cache. So that means when you are trying to generate gonna, you don't actually have to compute all the keys and activations of these previous tokens. So this is what it looks like with a KV cache. Okay, so there's going to be two stages, prefill. So you get the prompt, and you populate the KV cache, which is the set of key and value pairs that the transformer computes. And then you generate the logit, just the same computations we did before. And now you have the KV cache here, and then this distribution, which you sampled a token. And now you feed that through the transformer, which uses this cache, and then produces both the distribution of the next tokens, but a new KV, which is the basically activations corresponding to the token up. And then this gets fed in. So now you have the commented KV cache, you have these logits, you sample, and then that feeds to the transformer. You output the distribution of the next tokens, as well as the next, the new token, which you add to the KV cache, and so on and so forth. Okay, so the KV cache formally is for every sequence, so there's B of them. For every token, there's S of them. And for every layer in every head, you store a H-dimensional vector. Okay, and just to reiterate, for inference, there's prefill. You give it a prompt. You encode the prompt into these vectors. And this is parallelizable, just like in training, because you see the entire prompt. You can compute the KV cache. And then in generation, you generate the new response tokens sequentially. but at least you don't have to pay for generating the KV cache of the tokens that you already looked at. Okay, so is everyone comfortable with a KV cache? Any questions about this? All right, so let's try to figure out the flops and memory I/O for both the MLP and attention layers. So remember, S is the number of tokens we're kind of conditioning on, and T is the number of tokens we're generating. So we're going to do this sort of abstractly, and then later we'll specify to the prefill where T equals S and generation T equals 1. So for the MLP layers, and through all of this, I'm just going to look at the matmuls because the matmuls are the thing that actually require a lot of work. Everything else can be is not that many flops and can be potentially fused into the matmul too. Okay, so let's do this calculation. So it's the same as the matrix calculations. I'm not going to maybe step through every single detail here, but just the form is you read X from high bandwidth memory. You read all the parameters. You compute the up projection, and then you write it to HBM. You compute the gate, and you write it to HBM, and then you compute basically the down projection of that, and you write it to HBM. Okay, so the number of flops is depends on B and T and D and F. So batch size, sequence length, model dimension, and the feed-forward dimension, MLP dimension, and the bytes transferred is this expression. Okay, so now you can compute the arithmetic intensity, which again is flops divided by bytes transferred. So this is some expression. We're going to assume that, just like before, B times T is much smaller than D and F. And with that, then we see that the intensity is B times T. Okay, so this is analogous to just the matmul case. There's more matrices and there's like more dimensions, but fundamentally it's kind of the same thing, and it makes sense. An MLP is basically a big matmul. Okay, and it also makes sense because the batch dimension and the sequence length dimension are sort of everything is independent, right? And for the MLP, they don't interact. Attention's a different story, and so B times T. So as long as you have, in the prefill, if you make B times T large enough, large batches, long sequences, you'll be fine. Now let's look at generation. So remember, generation, there's two problems here. One is that generation T equals 1. Okay, you're only generating one token at a time, and so that means your arithmetic intensity is going to be B. But B, in generation, is the number of concurrent requests. And so if you're in a sort of batch setting, you kind of can control that. But if you're, let's say, serving a chatbot, the number of concurrent requests is essentially how many concurrent users there are, which can be high, it can be low, so it's a bit unpredictable. It can be changing over time. So that's something we're going to address when we talk about continuous batching. But overall, this is not bad, right? Because as long as you have large batches, the sequence length isn't going to really help you, but you have large batches, you should be good. So now let's look at the attention layer. So again, S is in the previous tokens already generated. T is the number of tokens you want to generate logits for. So in attention, you read the QKV matrices from HBM. You compute the attention. You compute the softmax, which doesn't really matter, and compute the value matrix, and then you write the result to HBM. Okay, so the flops is B times S times T times D, and the bytes transferred is this expression. So this should, all everything is a map model, right? So this should be always, 1 degree higher of a polynomial than the bytes transferred because it's a map model. The only question is, what does that factor look like? So that factor for attention is s times t over s plus t. Okay? So let's look at the prefill. So prefill, what this is saying is that the prefill intensity is s over 2 when t equals s. So this is good, right? Because as long as you have long sequence lengths, for attention, you're going to maintain high arithmetic intensity. Notice that the batching dimension doesn't happen here. I'll explain a bit, why later. But for generation, this is bad news, right? So the generated nation intensity is s over s plus 1, and that's less than 1. Or even, let's just call it 1. And arithmetic intensity, remember 1 is bad. We want it to be something like 295 for H100 to saturate the compute. And so, this is really the bottleneck. So we did all this analysis for MLP attention, prefill generation, and we found this to be a bottleneck. So let's try to contemplate why this is a bottleneck. So unlike MLPs, so MLPs for generation is actually okay as long as your sequence is, your batch is large enough. So the problem with this attention is that, let's look at MLPs. Every sequence hits the same MLP weights. Okay, so these don't depend on B. Whereas in attention layer, each sequence has its own KV cache. So these all depend on B. And so you can think about this as what's going on here is that in the MLP case, having B being big actually is helpful because you kind of get to load these MLP weights kind of once, and you can kind of use it for all your sequences. Right? That's how you get high arithmetic intensity because you use it, simplifying a bit, you load it once, you do all your batch processing, and then that is good. Whereas in attention, you can't, all of these depend on B, so increasing B doesn't help. It's like for every sequence, you're basically doing a map model. So they're all independent, so doing more map models isn't helpful. Just like if you remember in the very beginning, I showed you this example. This also has pretty bad arithmetic intensity. It's not a map model because we're essentially batching by a coordinate. And this is essentially basically the same as doing a dot product, which has horrible arithmetic intensity. And remember, this is in the attention. This B, blue B, is like the cause of why the attention is arithmetic intensity doesn't scale with B, and why that is a bottleneck. Okay, to just summarize here, so prefill is compute bound, generation is memory bound. So if you look at the MLP intensity for prefill, it's B times S, great. Prefill for attention intensity, S over 2, not as good, but workable. Generation MLP intensity, also workable, requires long concurrent requests, but it is really the generation attention intensity, which is a fundamental bottleneck, and that's it. You just have to, if you're sticking with a transformer, you can't really improve this. Okay, pause there for questions. So So now whenever you hear people say, oh, inference is memory bound, you know why. Okay, so let's now use these intuitions and calculations to think about our inference metrics, throughput and latency, and also TTFT. All right, so inference is memory bound. Now the main, in some ways this simplifies a lot of things, because when we think about how long things take, you just look at how much memory needs to be transferred. Okay, because assuming you overlap communication and computation, the bottleneck is going to be just the amount of memory that you have to deal with. Okay, so in some ways it's nice because it's simple, but in other ways it's frustrating that your accelerators are sitting there not doing anything. Okay, so let's walk through an example. So for Llama 2 13B on an H100, so what is the latency and the throughput? Okay, so remember Llama 13B has a particular shape. So this is the sequence length, the model dimension, feed-forward dimension, number of query, number of key value heads. There's no GQA here, so the NN equals K, head dimension, number of layers, vocab size, and the memory bandwidth for H100. Okay, so now using this config, let's compute the transformer performance statistics. Okay, so these are our inputs here. And just what the statistics I'm going to compute are going to be number of parameters, the memory, usage, latency, and throughput. Okay, so first of all, what takes memory? So the parameters take memory. So we compute the number of parameters. And so you look at the embeddings, the MLP layers, the projections of the KQV. At the end of the day, you get some number of parameters. Assuming that we're doing a BF16, which is always the case for inference, then parameters take up this many bytes. Also in memory is the KV cache. And the KV cache is the number of tokens in your sequence times the number of your heads, and the KV heads times the head dimension times the number of layers. You have one for the key and one for the value, and then you have multiple two for BF16. Okay, so that's the size of the KV cache. And the total memory usage is, this is for each sequence. You have B sequences, so that's B times that, plus the parameter size. And that's the amount of memory you need. And now, what's the latency? The latency is determined by the memory I/O. Okay, because inference is memory bound, assuming you overlap communication and compute, all the memory it's going to be on shuffling parameters back and forth between HBM and SRAM. So that's how long it takes to move memory around. Throughput is the inverse of latency, but we're generating B tokens in parallel. So this is this is tokens per second. This is seconds per token. This is tokens per second, as well as having an additional B because you're processing a batch of B. Okay, so now let's compute for this config. What are these actual values? Okay, so num parameters is 13 billion. So a good sanity check that it is advertised as a 13 billion parameter model. Memory is this term, which is about 838 million times B. So it's basically a linear function of B. plus some other term. So this is a KV cache, which grows as B. This is the parameters, which is double the number of params. Now latency is just this scaled by the memory bandwidth, so it has the same form as the memory. And throughput is B over that. Okay? So notice that latency, as you increase B, grows because the KV cache grows, and in order to process stuff, you have to copy the KV cache back and forth. And now throughput is more interesting because as you increase B, throughput does improve, but up to a limit, right? Because throughput improves because now you're amortizing the cost over a larger batch. But also, the speed at which you're processing this obviously is also increasing over time. So this sort of asymptotes. It's not going to, throughput can't possibly go to infinity. Okay. Any questions about this so far? So basically, you just have to remember latency is a linear function in B. This is where the constant is the size of KV cache, and then this is the number of parameters, and then throughput is some B proportional to B over B plus something. Okay, so now let's instantiate this for a bunch of situations. Okay, so if you have batch size 1, so this is what you would get. You get a latency of 0.008 seconds per token, and the throughput is 124 tokens per second. So what happens if you increase the batch size, you'll see that the latency goes up, but the throughput also goes up. So latency gets worse, but the throughput improves. So this is kind of an interesting thing because we think about, we just want to make it go fast, but fast actually has two meanings here, which actually, depending on which one you care about, is complete opposite. If you want to tune your batch size, that's going to really determine if you want latency or throughput. And what happens if you increase let's say we really want high throughput because we're processing lots of documents. Let's increase the batch size even more. Okay, so the latency gets even worse. It gets worse. Throughput gets even better. But the main problem here is that your memory, you run out of memory. Okay, because the memory for storing this KV cache is going to exceed your H100 memory. And if you have B200s, you can increase the batch size more, but eventually you hit some sort of limit. So there's kind of limitations to how much you can in through your throughput. You'll never get to sort of the asymptote because you'll hit the memory. Okay, and also your throughput, is getting, your gains are kind of diminishing as well. So increasing batch size worsens the latency because now you have a larger KV cache to read and write. And remember, it's batched, so if you're an individual query, you have to wait for everyone to finish. So you have to basically, you're like waiting for a bus, and the latency is pretty high. You wait, and then you go. Whereas the throughput of a bus is pretty good because you can move everyone at once. So the throughput improves as batch size increases because remember the parameters are shared, and you load that once into memory, and you can process a lot of sequences. Okay, so trade-off between latency and throughput, just to make sure everyone's aligned. Smaller batch sizes use better latency but worse throughput. Large batch sizes yield better throughput but worse latency. Okay, I'm not going to really talk about parallelism too much. There's also another dimension of inference, which is you can shard your model across multiple devices. You can look at the scaling book chapter on inference if you want to know more. Just as a kind of a very trivial example, if you launch 5M copies of the model, the latency is the same and the throughput increases by M. And then the other metric we didn't talk about is time to first token. And this is essentially the time it takes to do prefill. Because after you finish prefill, then you can basically start generating. Okay. So if you want, if you want, faster TTFT, you should use smaller batch sizes, and you want larger batch sizes to improve throughput. Okay. So hopefully that is clear. Any questions about throughput and latency and how they're in tension with each other? Okay, so now that we have a conceptual framework for thinking about how efficient inference is in terms of arithmetic intensity and throughput and latency, now let's try to make it faster. How do we make inference faster? There's a bunch of different techniques which are quite varied, ranging from changing the model architecture to doing systems optimization, everything in between. So inference in some sense is a fairly rich cross-cutting topic. Okay, so the most kind of maybe now in hindsight obvious thing you can think about is hopefully beat it into your head that memory is the bottleneck for inference, and the KV cache takes up a lot of memory, and it could even be larger than the number of parameters if for a large enough batch size. So let's just try to reduce the size of the KV cache. Now, you have to be careful about how you do this because you want to make sure you don't lose too much accuracy in the process. So here is one thing you can do, which we already talked about, which is grouped query attention. And just as a kind of a reminder here, so multi-headed attention, basically for every token you have a key and a value and a query. And if you do grouped query attention, you basically compute the same number of queries, but you have only a smaller number of groups, and you compute key and value for each group. Okay, so K is a number of groups here. And so in the multi-headed attention, K is n, no reduction. There's something called multi-query attention, which no one uses because it's really bad. K equals 1. And somewhere in between is hopefully where we'll find a balance between accuracy and speed. So there's this is the paper that introduces GQA from 2023. And they show that if you look at time per sample, which is related to both latency and throughput, you see that the MHA, so multi-headed attention, full attention, has this high time, whereas if you start K equals 1, it's much faster, and then you can actually keep on increasing the K to K equals 8, and it's still pretty good, and eventually your time goes up quite a bit. Okay, so why does GQA improve the latency and throughput? Well, it reduces the KV cache by a factor of n over k, just as a friendly reminder, reducing memory usage leads to speed up because we're memory bound. Okay. So let's revisit our friendly llama model here. Remember, in the initial configuration, we're just using k equals n, so there's no multi-headed. There's multi-headed attention, no reduction in number of key and values. And so for this one, remember using a batch size of 64, we get this throughput and latency. Now, if you do GQA, we're going to put in, let's say, a kind of a sparsity of 1 to 5. That reduces the memory quite a bit, which in turn improves the latency and also improves the throughput. So it's not that latency and throughput are always at odds. If you reduce the amount of memory, then it improves both. It's mainly the batch dimension that allows that is the point of tension. Okay, so this is great, and let's actually just increase the batch size even more and see what happens. So before, if we had a batch size of 256, we ran out of memory. But now it fits in memory, and we see that the latency suffers a bit because we're increasing the batch size, but the throughput goes up proportionally. Okay. So sometimes you kind of play with these parameters jointly. Like you can reduce the KV cache, but that allows you to increase the batch size and allow making other trade-offs. So the final thing you have to do whenever you do some lossy change is that you make sure the accuracy doesn't drop. And this paper shows that for GQA, the time is better, but across a bunch of evals, basically it works well. So now, with these accuracy evals, I think you always have to take it with a grain of salt because this is like for a particular model. Later, the DeepSeek paper was to show that it actually does hurt. So, I guess take everything that's not just kind of math with a grain of salt here. Okay, so speaking of DeepSeek, here's another idea to reduce the KV cache. Okay, so the theme is reduce the KV cache and latency and throughput improve. So this is multi-headed attention, same number of queries and keys and values for every token. And GQA, remember, we have reduced the number of keys and values for every token. Sorry, not for every token. We basically have reduced the number of values and keys. And now the multi-latent attention for DeepSeek says we're actually going to leave the number of keys and values the same, one for every token essentially. But I'm going to compress these. So normally you have some. How do you compute your keys and values? You have your activations, and you multiply them by some matrix to get k, and some other matrix to get v. And these are generally n times h dimensions, like your model dim, which is big. So MLA says I'm going to actually project these activations down into C dimensions. So DeepSeek V2 reduced it from 16,000 to 512. So this is quite aggressive compression here. And then I'm going to compute the K and the V from this compressed representation. So now I can just store C. This is much smaller. And then when I need my keys and values, I can just materialize them. So there is one wrinkle here, which is that MLA is not compatible with ROPE, which operates directly on the keys and values. So what they do is add additional dimensions for handling the ROPE. But more or less, it's still a pretty big reduction. So the latency and throughput improvements follow by just simple math. The smaller the KV cache, the faster you go. Okay, it's almost kind of linear scaling up until some point. And then remember, you need to check whether your model is accurate. So first of all, this is sort of the result that kind of contradicts or is in tension with the GQA paper. They show that GQA actually isn't that great. It's much. So this is MHA. This is GQA. These numbers are smaller than these numbers. But they show that their method, MLA, multi-latent attention, works even a little bit better than MHA. But let's just say it's about the same. So this column and this column are much better than. I guess there's no GQA on this table. It's to compare over here. Okay, so I'll show you question.
How does this compare to reducing the number of dimensions to model?
So the question is, how does this compare with reducing the dimension of the model? So that's a good question. These ablations don't show that. My guess is that reducing the model dimension just makes things worse because you're sort of like indiscriminately just like reducing everything. I think the trick in all of this kind of is to find places in the model where you can squeeze. And this a priori, I don't think you can necessarily know for sure. You just have to do a bunch of experimentation and see what works. So here's another idea to reduce your KV cache. This is called cross-layer attention. So the idea is that normally every layer has KV, Ks and Vs. But let's say instead of doing that, we're just going to compute KVs for a subset of the layers, and then just for this layer, I'm just going to use the previous layer's KV cache. Okay, so this is kind of another way of sharing. Just like GQA shares KVs across heads, now I'm sharing KVs across layers. And empirically, this paper shows that doing this improves the Pareto frontier. So each of these models is better than given a method, you can always kind of sweep the size of the KV cache by changing the K and the head dimension, which I guess kind of relates to your point about changing model dimension. But if you do this CLA, cross-layer attention, it's better. Okay, so let me give you, moving on, whirlwind tour of different techniques for reducing KV cache. There's local or sliding window attention. This is a fairly kind of old idea and a very kind of natural idea. So if you look at the full attention matrix is n squared. And instead of doing that, if you're going to generate a token, you just look at the last k tokens. Okay, so you essentially have a sliding window for every token you generate. You just depend on the last k. And now, if you do that, the effective so the KV cache is now independent of the sequence length. It's just the number of the batch times the other variables, which is great, and this is especially great for long context. Now, because of the number of layers, the effective context length is actually larger than the number of the stated context length because information can propagate farther if you go down the layers. Now you can do fancier things, like you can maybe not do a dense selection of layers, but you can space it out. You can also do this global plus sliding window where you have attention to a fixed grid of different token points plus a local sliding window. So you can do various things. Now the problem with this is that it actually still hurts accuracy. So this reduces expressivity. There's no free lunch here, or at least this was an expensive lunch. So the solution that people come up with is that they interleave local attention with global attention. So these hybrid models have full attention for some of the layers and some local layers for some of the other layers. And you're basically always trying to, and then so that allows you to essentially reduce the KV cache a little bit, and you're always trying to balance accuracy with speed. Yeah.
Model-wise, is there a difference between the trade-off of using like a linear attention variant versus like a sliding window?
Yeah, so the question is, what about linear attention versus sliding window attention? So I'm not going to talk about linear attention, but very quickly, there's a bunch of methods where instead of storing a KV cache, is you basically compute some sort of like compressed representation of all the history. So the most naive linear attention is you just sum the KV values up into a single vector. So that's definitely independent of the sequence length. You can do fancier things. There's like GateNet, Delta Nets, and Mamba, which allows you to try to compress but not forget as much. Now the question is, how do those compare? Those have also been used in place of sliding window attention, and people have gotten good results with them. You can also use a combination of full attention, sliding window attention, and the linear attention because they sort of capture different aspects. If you care about kind of local, kind of high resolution stuff, then sliding attention is better. If you just kind of want like broad summaries of the past, then the other, the linear attention might be better.
So then for like a long context sense, would you say linear attention would be a better setting for that?
So the question is, for long context, would linear attention be better? Let me talk about, so there's no free lunch, right? Like I think, let's say you have a very long context and you're sort of solving a needle in a haystack problem, right? If you have to compress your entire history into like a small context, you're just going to lose information, and you might just not be able to retrieve it.
I guess I feel like what it seems like people go with hybrid architecture that you'll always need some sort of longer attention, but I'm just trying to understand like in my head like what the trade-off between using a sliding window versus like some sort of Mamba delta net layer would be. That like is using a delta net layer like better than using sliding window consistently, or like what is the actual like maybe representative trade-offs?
Yeah, I guess maybe I'll say that the Mamba and delta net are more powerful than the sliding window attention. Maybe you can think about the Mamba as it probably can, like it certainly can represent some of the aspects of sliding window attention because like you can just, as you're doing the recurrence, it can just look at the last state. So maybe you can think about the linear attention or its like extensions as being better. At least they have more room. Like once you do sliding window attention, like you're done. There's nothing else you can. Yeah. Okay. So let me just quickly go through this. Just highlight this. DeepSeek. DeepSeek continues to innovate different types of attention mechanisms. So remember, they came up with the multi-latent attention, which compresses the key values. There is this thing called, now they have compressed sparse attention, DeepSeek sparse attention, and heavily compressed attention. I never kind of remember all these acronyms and what they mean, but let's look at this diagram. So normally you have your KV tokens and your query token. So compressed attention is going to basically compress every M tokens into one token. And then there's this thing called DeepSeek sparse attention, which basically selects a subset of those to kind of keep. And the way you select a subset is that you actually compute some lighter weight queries and keys, and then you do like a smaller attention to get these index scores so you know what to keep. So like a kind of a lightning fast way to figure out what tokens you need to keep, and then you use those. And then there's a more compression that happens. So in the interest of time, I'll move on. The goal of this section is to reduce the KV cache because KV cache is related to memory, and we saw that inference is memory bound, so that directly translates to improvements in throughput and latency. And the key is to do this without hurting accuracy. So you can do lower dimensional KV caches across layers across heads and across head dimension. You can do local attention. You can do linear attention, which was discussed earlier. And there's much more. And also there's also diffusion models, which is a non-autoregressive way to generate, which can be much faster. Okay, so let's talk about a few other ideas which are important. So quantization is more of a, I would say, less of an architecture and much more of a systems perspective on how to make things smaller. So the key idea here is just reduce the precision of the numbers. Less memory means higher latency and throughput. And obviously you have to worry about accuracy. So quantization is, there's many options here, all the way from BF16 all the way down to Int4. And so one thing you can do, if you're kind of scared that quantization is going to mess you up, is that you train a model with quantization in mind. So this is called quantization-aware training. And during the feed-forward pass, during training, you quantize and dequantize, and you're basically simulating these quantization errors as you train. So then generally, now the weights are adapted towards the quantization, things will work better, but the con is that it requires expensive large-scale training. And typically what typically people do is they train models and then they quantize after the fact. So this is post-training quantization. It's much cheaper often. There's a naive way to do it, is that you basically, for every layer or tensor, you basically determine the scale and the 0 point for each, let's say, tensor, and then you quantize that separately. This is generally doesn't work as well. You can use this idea called GPTQ, which uses some Hessian information to quantize layer by layer, and then you keep track of the errors which get propagated into the non-quantized weights, and so it kind of allows you to correct for the errors. And now activation-aware quantizing is more kind of a sophisticated way, where the observation is that some activation channels are large, and the weights that interact with those matter more. So let's allocate more precision to these weights. So let's look at this picture. So normally, if you take FP16 weight matrix and you quantize it, you get, let's say you're quantizing down to N3. But what you're going to do is you figure out which of these so these are maybe activation channels, and some of these activation channels are large. So if they're large in general, then you basically allocate, let's say, FP16 for this channel. You keep everything else as Int3, and for a few important channels, you use higher precision. Okay, so another idea here is to do model pruning. So here you just take a large model and you rip out pieces of it and you fix it up. It's kind of a very crude way, but it turns out to work. So there's this paper from NVIDIA where essentially, let me actually, let's see. So you kind of first have to estimate the importance of the different parts of the model, and choose the most important parts, and then you basically remove different hidden units and different even layers, and now we have a model. It's not going to be very good, and so what you do is you post-train it, you train it some more on the data or the tasks that you care about to kind of heal it. Okay, so this is in some sense a training way to reduce the KV cache, but where you sort of initialize it with parts of a good model. Okay, so this seems to work pretty well. So they were able to take a 15B model and reduce it to an 8B model, and it doesn't really hurt accuracy by too much, and the amount that you use to kind of train the model or through this process is much less. Okay, so just to summarize here, the game is to reduce the inference complexity without hurting accuracy. You can think about this as mostly reducing either number of parameters or KV cache. You can define a faster model architecture to train it, or you can define a faster model architecture, initialize the weights from original model, which might have a different architecture, but you kind of just make this Frankenstein thing, and then you repair the faster model with distillation. Okay, yeah.
More about how you distinguish the important layers from the unimportant layers?
So how do you distinguish the important layers from the unimportant layers? So in general, you have a calibration set, and you pass the inputs through the model, and you're basically looking at the magnitude of the activations, and the ones that are some of them, especially if they're dead units, will be kind of close to 0, and the ones that are large you want to keep. So that's a high-level idea.
I guess why does it matter if the activation is high? It could just be like what if it's just always high, for instance? Or is that?
So in general, okay. So the question is why? What if all the activations are high? So in general, this is a kind of empirical observation that some of the channels will be much higher than others. If this weren't true, then these techniques wouldn't necessarily work. But it happens to be true because that's how these models ended up being trained, and then you can exploit that.
Or I just made it this, say a neuron which is always value 100 for across all the samples.
Yeah.
Would that mean that it's necessarily meaningful, or maybe it's just an artifact of training that I'm just put into?
Yeah. I see. So the question is, what if a neuron is always 100? I mean, if that's the case, you can also look at kind of variance related questions. Like if it's 100, you can't just remove it because then everything is going to be broken. But you can, if it's high mean and low variance, maybe there's another, a way to just incorporate the bias essentially. Okay, let me quickly go through this other idea. So far we've looked at lossy methods, which basically kind of really crunch down the KV cache, but it could hurt accuracy. There's a very elegant way of doing this in a lossless way. This is called speculative sampling or speculative decoding. So remember that if you're doing prefill, you can code all the tokens in parallel. And this also gives you probabilities. This is fast. This is compute bound and all nice things. And in generation, it's one at a time. Okay, so checking is faster than generation. If I give you a sequence, it's fast to tell me how good it is, much faster than it is to generate one at a time. Okay, so you can exploit this asymmetry using the following idea. So what we're going to do is use a cheap draft model to basically generate from. You guessed a few tokens, let's say 4 tokens. And then we're going to use the model we actually care about, the target model Q, which to basically review these tokens and accept or not accept them. Okay, so things are kind of chosen to be balanced. The draft model is smaller and cheaper, and so even though it's memory bound and it has to generate one at a time, it's not too bad. Whereas the target model is big and expensive, but what we're doing is asking it to process a batch of tokens in parallel, so it won't also be too bad. Okay, so here's the video that shows kind of how things work. So if you use a big model, token by token, it's going to be pretty slow. But if you are doing speculative decoding, then you can see the small model kind of generating a bunch of tokens, and then the large model basically critiquing them, and then so you basically can get this sort of burst of tokens, and then maybe another burst of tokens, and so on and so forth. Okay, so here is the algorithm for. There's a few papers that came out with speculative decoding around the same time. This is one of them, and so the idea here is that in order to generate, we're going to generate k tokens, and we're just going to sample from this draft model. So P is the draft model. We're going to sample k tokens, and then in parallel, we're going to compute the logits of these draft tokens using Q. And then now we have to determine whether we accept or not. And this is where you do a bit of math and probability and statistics. You basically are going to accept with probability min 1 over this ratio of Q over P. So if Q is much larger than P, the larger the Q is, the more likely we want to accept it. And otherwise, you kind of sample from this residual distribution and exit. Okay, so this is basically rejection sampling, except for in rejection sampling, sometimes you just when you reject you get nothing, but here we always are guaranteed to get an exact sample from the target model. I'm going to skip this kind of simple proof. It's basically the same arguments as kind of rejection sampling to show that it's the exact probabilities from the target model. And the initial paper shows that this is this fast. And generally, if you look at if you have too few draft tokens, you're not really leveraging the batching on the target model side. And if you have too many, then you're going to reject more often. So there's a sweet spot around, in this case, 3 or 4. Okay, and in general, the draft model is much smaller than the target model. And ideally, you want the draft model to be as close to the target, which means that you want to kind of distill it. So which means that actually a lot of the same ideas that we just talked about are applicable to speculative decoding as well. So basically the idea is that let's try to reduce your KV cache via all the different shenanigans. And if you end up with a model you're happy with, just serve that. If you're not happy with it, then it at least can be a draft model, and you can use your main model to fix things up. There's a bunch of whole literature on speculative decoding right now that improve over the original, which I'll kind of skip for now. Okay, so very quickly now, dynamic workloads. Okay, so this is the use case is you're serving a live website and users come and chat with your model. The requests arrive at different times. They have different shared prefixes and they have different lengths. So it's kind of pretty messy. It's far from this kind of very simple training where you have these blocks of the same number of tokens all at once. So what do you do in this case? So there's this idea, there's a system called Orca that was built. This is actually very early on, which introduces this idea of continuous batching. So the idea is that you get a bunch of requests that look like this. So here's a prefix of the first request, and you're generating this token. Here's the second one. Here's the third one and fourth one. It's jagged because every prefix has a different length. And what we're going to do is we're going to decode step by step. So every step, you decode one token for all the sequences. Next step, you decode another token for all the sequences. And then if you end, you just eject that sequence. And then as new requests arrive to the batch, then you basically put it in the batch, and then you just kind of continue. So that's why it's called continuous batching, because it's sort of this, your batch is dynamically being updated with either old finished sequences being evicted and new ones coming in. So now one problem here is that everything we've seen, batching works when all the sequences have the same dimensionality, right? You have tensors, every slice has the same dimensionality. But each request here has a different length, so what do you do about that? So there's this idea called selective batching, where let's say you have a length 3, length 9, and length 5. So here, in the attention computation, you can't really do anything about this because attention sort of depends on the length of your sequence. So if you have a 3 by 3 computation, a 9 by 9 computation, you can't really share the tensor effectively. But for the non-attention, the MLP layers, which is takes up a lot of flops, you can actually just concatenate all the sequences together to form a mega sequence, and you process that. Okay, so final idea is page attention. This was introduced in the VLM paper. Of course, VLM has many other bells and whistles now, but this is kind of the core idea at that time. So, so the question is, how is the KV cache stored, right? So if you think about requests coming in, you have to put them in memory somewhere. And in general, there's this problem that you get fragmentation. This is what happens to, or used to happen to your hard drive, and you have to defrag your hard drive. Back in the day. So there's two types of fragmentation. One is that you have to allocate enough buffer so that, because you don't know a priori when you're going to stop. So you might have a max token limit of 1024. So you have to allocate all this memory, and you can't put anything in there because you're going to just generate until you hit the max tokens, and that's very wasteful. That's internal fragmentation. And then there's also there could be space between different requests, and that space is maybe too small to get used effectively, so that's just wasted space. So the solution here is just, these are systems people, so they know their operating systems. They said, okay, well, we've solved this problem once before, so let's just use the same idea here. So we're going to divide the KV cache of a sequence into non-contiguous blocks. Okay, so if you have this sequence 4 years ago our fathers brought forth, we're just going to chunk it up into these blocks of size 4. Doesn't matter where the blocks go, but they're going to be kind of aligned according to the blocks. So there's some uniformity there. So when two requests can actually share the same KV cache. So you might have this block and this block. So this block might go here, and this block might be over there. So they're in kind of interspersed, but as long as you have the indices and keep track of where everything is, it's fine. So in particular, if you have system prompts, then you can actually just cache these system prompts, the KV cache and the system prompts once, right? And that can be useful for all the queries. Okay, so this is very useful because if a lot of people are using the same system prompt, then you don't have to compute the KV cache for every request. Also, there are many applications where you have the same prompt and you actually want to generate multiple responses. So in that case, you can also just share the KV cache for all for the prompt and just have unique responses coming out. Okay, so for example, if you were to generate, let's say, multiple generations from 7 years ago R blank, and so what would happen here is that you would have 7, and you would start by having years ago or hour, and then this is called copy on write semantics. You keep this, and then we have these two samples, and if they had happened to sample let's say the same token, you just continue with that. But if they sample different tokens, you split a block, and then you can kind of continue there. So you're basically sharing as much of the prefix cache as you can. There's a bunch of other optimizations like kernels that I'm not going to have time to go over. But the general idea is that you're using kind of these operating systems, metaphors to manage kind of your inference. Okay, so summary here. Inference is really, really important. It's very different from training, even though it's the same model, but you're asking the model to do something very different. It ends up being very memory bound, and it's also dynamic if you're kind of in a live chatbot use case. We saw a variety of different techniques to improve inference. You can quantize, you can come up with new architectures, you can prune and distill, you can also use speculative sampling. But all of these are driven by the same principle here, which is reduce your KV cache, but don't hurt accuracy too much. And then there's ideas from systems like paging and speculative execution that can be brought to bear for actually live kind of inference servers. One thing we didn't really get a chance to talk about, which was discussed briefly, is that I think that new architectures have actually a huge potential for improvement. Things like state space models or linear attention or diffusion. These can, at some level, the KV cache and the way that attention is built fundamentally makes it an inference unfriendly kind of architecture. So if you can come up with a new architecture that is sort of designed for inference in the way that the transformer was not, this can maybe unlock a lot. Okay, so I will stop there. And next class, Tatsu will return and talk about scaling laws part 2.